Hey everyone. So in this video I like to talk about concavity. So during our last discussion we defined a few terms for a function. We said that a function is increasing if the outputs increase as the inputs increase. And graphically this amounts to the graph traveling upwards from left to right. And we also define when a function is decreasing, and really you can kind of imagine that as a graph traveling downwards from left to right. That's when your graph is decreasing. And for these terms, we're mainly concerned with when a function is increasing or decreasing. In other words, what intervals of the input is the function increasing or decreasing. So I'd like to talk about another behavior and give this a little bit of attention for functions. This behavior is called concavity. And so here, let me sketch two examples to illustrate this idea. So let's say we're looking at a lake and there's some toxic algae in the lake. Right? So as the days go on, the amount of toxins produced by this toxic algae is going up. So, maybe here I've got one graph of the amount of toxins produced by that toxic algae in the lake. And then here I've got another graph. Oh no, let me actually do it this way. So here's another graph of the amount of toxins in the lake produced by that toxic algae. And so one thing to notice is that in both of these graphs that I've sketched, they're both increasing functions. The graphs are going upwards from left to right. Right, so these examples, they're both increasing functions. But they're increasing in different ways. I mean, if we look at these pictures, which one looks a little bit more worrisome in terms of how much toxin is in the lake? Well, this one on the left looks a little more worrisome because we can kind of see the trajectory that it looks a little bit like the amount of toxins in the lake is increasing in a more steep fashion. It looks like it's going to get more toxic. And we can kind of define that by looking at the rates of change of these two graphs. Right, so if I look at the rates of change of this first graph, so here maybe, we talked about the average rate of change as being kind of the slope between 2 points on your curve, on your function. And if I look at the average rate of change between a few different points, we can see that the average rate of change is increasing. Right, so for this left graph, we said that, here, let me write this down, the rate of change of the left function is increasing. Whereas if we look at the rate of change of the right graph, the graph itself, the function itself is an increasing function. It's moving upwards as the graph goes from left to right. But if we look at the rates of change, at the average rate of change, I can kind of sketch that between a few different points. And we can kind of see that average rate of change is getting less and less steep. It's going downwards, or it's decreasing maybe I should say. And so the rates of change of this left function is increasing, but the rate of change of this right function is decreasing. And these are important points to distinguish because they kind of describe different behaviors of the graph. And so we give these two different kinds of behaviors names. We say that a graph exhibiting this behavior, we say it's concave up. And a graph exhibiting this behavior, we say that it's concave down. And if there's any point in which your graph changes from being concave up to concave down, we call that an inflection point. Right, so when your graph changes from concave up to concave down, or the other way around from concave down to concave up, we call that point an inflection point. So I illustrated concave up and concave down, these two qualities of a function for increasing functions, but these ideas, they also apply to decreasing functions. Right, so here maybe let me draw another graph here. Let's say it looks something like this. Right, so this function's decreasing, it's going down from left to right, but the question is this concave up or concave down? I encourage you to pause the video and take a moment to think about this yourself. So if we look at the average rates of change of the points, between the points on this function, on this graph, well, here's maybe one example. Right, the average rate of change, again, it's the slope between 2 points on your graph. So that's one example, and here's maybe another point, or another pair of points, which we can sort of look at the average rate of change between. And we can see that the original, the first example that we drew, the first slope that we drew more on the left side of this graph, it's a little more steep downwards. It's more negative, right? And then the second average rate of change, it's a little bit less negative. It's a little bit less steep downwards, right? So here, from left to right, we can kind of see that the average rate of change is less negative. Where it's pointing downwards in a less steep fashion. And another way of saying something's less negative is that that quantity's increased, right? So this is like saying that the average rate of change increased. It's less negative, it increased. And so this is an example of a concave up function. So what about this next example? Let's say I draw it like so. Let's say I draw it like this. So again, this function's decreasing, and if we measure some examples of the average rate of change between a few different points along this function, so the first example we drew, was more flat, whereas the second example we drew was a little bit more pointed downwards, a little bit more negative. And so here, this is an example of a concave down graph, or concave down function, because the slope became more negative, pointed downwards more, going from left to right. So this was a more negative slope. In other words, the rate of change is decreasing, right? Something becoming more negative, I can think of that as decreasing. Right, so this is concave down. So we can often recognize when a function is concave up or concave downwards by looking at the shape of the graph. So often when a graph is concave up, it looks sort of cup-shaped. right? It sort of bowls upwards. If we look upwards towards this function that we called concave up, you can kind of see that it opens upwards a little bit. Whereas a concave down function so I've seen this described as hat-shaped. It sort of bowls downwards, right? Kind of in the shape of a hat. And if we look at our previous example, we can kind of see that it sort of curves downwards. And we can sort of see this in our previous examples as well, right? This left example was an example of a concave up function, and it sort of bowls upwards, whereas the right example bowls downwards, and we called that concave down. Okay, so let's go ahead and apply these ideas to this graph below. Let's identify what intervals of the input is this graph concave up, and what intervals of this input is the graph concave down. And we can kind of see here that this first chunk of the graph that's concave down is along this part here. Right, so this part of the graph is sort of bowls downward, looks like a hat a little bit, but we can be a little bit more precise by noticing that if I sketch the average rate of change between points, 2 points on this part of the graph, well, it goes from pretty steeply increasing to less steeply increasing. In other words, that rate of change is decreasing. Right, that slope decreases, and then if I keep going, well, I see that it continues to decrease. But then after that point in red, we can kind of tell that the average rate of change between the points on the graph are going to increase, right? Because this graph sort of bowls upwards. Here's an example of the average rate of change between 2 points on this graph, and I can see if I were to pick 2 later points on this curve, well, that slope has increased quite a bit. It went from being negative to being positive. And so here, we would see that those slopes are going to increase, up until this point here. And then the slopes are going to start decreasing again from here onwards because it starts to bowl downwards again. And when does that change? I would say about here. Right? At that point, it starts to look like it shifts from opening downwards to opening upwards. And so here, this would be the concave up portion of the graph. And so here, if we want to label all of these, I would say that here we're concave down on the intervals from -3 to 2. We're talking about the input interval from -3 to 2, union 4 to 7. Now what about concave up? That's from 2 to 4, union, this is 7 to 10. Okay, maybe let's take this a little bit further and remind ourselves of a few ideas that we introduced in the previous discussion. So we also talked about increasing and decreasing parts of a graph, and we also talked about local maximum and minimums. So let me ask you to take a moment and find those. So find the intervals of increasing and decreasing, and then find the local max, the local maximums, and the local minimums. So pause the video and give those a try. So the graph is increasing along this portion here and along this portion here. And so I would say the intervals in which these are increasing, this function is increasing, is from -3 to 0, 3 to 5, and then there's one portion that I guess I left out here from 9 to 10. So here it's increasing from, what was this? This was -3 to 0. Union 3 to 5, union 9 to 10. What about the intervals of decreasing? Well, those are occurring along this part of the graph here. And so that's happening from input values between 0 and 3 and between 5 and 9. So from 0 to 3, union from 5 to 9. These are intervals in which the function is decreasing. And what about local maximums? Well, local maximums occur when the function changes from increasing to decreasing, right? We can see that there's kind of this little peak here where the function changes from increasing to decreasing. And when we talk about local maximums, we're talking about the y values, the output value. So here we have an output value of 4. And similarly, we have another local maximum here at this point. See, that's another point where the graph changes from increasing to decreasing. And so here we get another local maximum at a y value of 3. Maybe I'll label these slightly differently so it's not interpreted as a point. Y is equal to 4, y is equal to 3. What about the local minimums? Well, they're sort of the other end of the spectrum when our graph changes from decreasing to increasing. So we get one local minimum when y is equal to 1, and another one when y is equal to, what is this? This is -5. So I have one last example here that I like to talk about. I've got a function depicted by the table below, and I want to determine whether this function is concave up or concave down. And if you're up for it, please give this a try, and we'll talk about this together in just a moment. So a function is concave up if the rates of change of the function between pairs of points is increasing. And a function is concave down if we examine the rates of change between the pairs of points and that rate of change is decreasing. And so let's go ahead and find some rates of change. Let's look at each pair of points and determine the rates of change. So here, the rate of change between these 2 points would be, -4,000 per 5, increase of 5 in t. Right, actually, we don't have to go ahead and compute this because all of the changes in these values of t are by an increase of 5. So we can sort of just see what the changes in the outputs are. So here, this is a change of -3,000 per increase of 5 in t. This rate of change here is -2,000 per 5 units increase in t. And then this last one is -1,000 per 5 units increase in that input variable. And so if we're looking at the rates or how this rate of change is changing, we can see that these values are increasing. Right, so this rate of change is increasing. And so although this function is a decreasing function at the end of the day, the values are going down, the outputs are going down, the rate at which it's decreasing, or the rate of change of this function is actually increasing. Right, that decrease is slowing down. And so here, we're going to call this a concave up function. And if you would graph these points, if you were to plot these points on some coordinate plane, you would be able to see that it sort of bowls upwards, like we expect for a concave up function.